streaming now, and we'll get the little Twitch control channel up in case anybody wants to
Yeah, maybe
chat
this
with
is
us. And we're back to programming Bitcoin. I did not refactor anything, so that might be just the thing that we do first, or we can try to talk about that section of the book that you called out earlier.
I thought that would be cool, man, because
Okay.
I read that like 4 times, but still.
Yeah. I read it a couple times today just to try to like wrap my head around it. I think there's some key takeaways that sort of make it easier to digest. So we're kind of skipping here a little bit. We're going through a big refactor, needing to use the big wint for everything. And yeah, we were gonna have to go back through and refactor all of our point calculations, because if we run our tests, I think everything previously was written for U64, which doesn't work when you're working with like really, really big numbers. So if we run the whole cargo test, it tries to build it, and we're just gonna get so many errors, and most of them are gonna be like, "Hey, this is a big win, and you're giving me something else," or something to that nature. So we can just stop that and not worry about that now. But what you had brought up earlier in our chat was page 61 through 65-ish, I think,
Mm-hmm.
where it talks about public key cryptography, which I understood public key cryptography before Bitcoin from like a SSH key perspective, because well, it's not so much public key cryptography, but it was asymmetric keys, right? So that public private key pair, they are asymmetric, meaning the one you can do things with one, but you can't undo the thing with the other, if that makes sense. So if you do a thing with the private key, the public key can verify that was done by the private key, and vice versa. So if you encrypt something, so like in basic asymmetric cryptography for like public private key pairs, if you sign a message with a private key, you can validate that message with the public key. If you encrypt a message with a public key, you can only decrypt it with a private key, right? And so that sort of basic fundamental building block is what Bitcoin's built on top of. But instead of, well, no, not instead of, you're actually signing a transaction, right? You're signing a script with that private key, and you're using a public key as a, you're signing with a private key to prove ownership over a public key that you had previously generated, right? Because that's what a Bitcoin address is a public key generated from your private key. And I think this is, and what this next section of the book gets into is how that public key is generated and how that asymmetry works with the public and the private key. So you create a public key as your address, and you're signing a transaction to prove that you own this UTXO that was addressed to that public key, right? Are you tracking?
Mm-hmm.
Okay.
Yes.
And then when you want to spend or transfer that UTXO, you have to then you're signing a new transaction, but you're giving it a new public key, and that new public key is now the target, right? And this goes into a whole story about like signing and verification, about shooting an arrow, and basically you're inscribing the target on the tip of the arrow, and then you hit the target, sort of thing. And the inscripting the target part, where is this signature algorithm?
Mm-hmm. CDSA.
Yeah, elliptic curve digital signature algorithm. And it deals with so we're gonna have to keep track of, and I'll create a little note over here because this I was doing this with like pen and paper earlier, and I found it really helpful to kind of like follow along because it references a lot of these static variable names like P and E and G and all these other things, right? So we'll just keep notes off to the side.
Yeah, I think it would be cool. Yeah, these notes, and then mark which ones are static, which ones are related to the keys themselves, which ones are related to the transaction. So you know,
Okay.
there's some stuff that is decided on the time of the transaction.
Right. Yeah.
The
No, that's
random number.
so we have E, which is our private key,
Mm-hmm.
right? And this is something that we never want to reveal ever. And it even goes into there's a way like, well, we'll see how it goes, but there's a way, the way you don't divulge E is through the discrete log problem because it's really hard to reverse the scalar multiplication. Right? Do you remember that?
Yes.
Where was that at? Let's look up the discrete. Where? Yeah. Okay.
49.
Page 49. Yeah. So this is the discrete log problem, and it's basically reverse. It's nigh impossible to reverse scalar multiplication without just a serious amount of power. Oh no, my video went out. Sad. Oh well, nobody needs to see me. So yeah, that's a thing.
Yeah, interestingly, yeah, it's a reversing scalar exponentiation in a way. Because when we do lots of multiplying, that's the same as exponentiation. And the log is the reverse of the
Right.
exponentiation, right?
So go back to
So,
this. We have E, and then we have P, which is our public key. And if I'm understanding this correctly, we are generating P by multiplying E times G. Now do you remember where G is derived from?
G is the generator point for the Bitcoin curve, right? The
Yeah.
SECP 256K.
Yep. Yeah, and it's these two really big numbers are the X and Y of G.
Those are the generator. Those are the coordinates for the generator point.
Right.
Yeah, and I found it interesting that for the private key it's just an integer, single 256 bit number.
Yeah, where does that? Yeah. So nice. Yes.
The public key is a coordinate.
Right. And they're each 256.
Yeah.
And then G is the generator point of SECP 256K1. Okay, so we got these defined here. And then the target, and this is something that I didn't quite get. I guess it's like you just pick a target randomly. So K, or K times G rather, is going to give you this R number, this uppercase R.
Which is a new number, huh?
Yeah.
variable new factor.
Um, and then R becomes the actual target, but we only care about Rx. Okay.
We do the static. These are static.
Okay.
These are transaction related, right?
Yeah.
Signature related. We're building the signature, we use these numbers. We'll fine tune it as we go.
So, and then we have, so this is where it kind of gets
I have a cat trying to eat my headphone wire. Okay.
This was the following the math again takes a little bit of brain power. And so this is talking about the point at this is equivalent to the discrete log problem. And so G and P are no P. Oh, what was P? P is our public key, right? Or yes. So G and P are known. U and V are chosen by the signer. And so that's what I don't know where or when that happens. But we can animate that. And they cannot be 0.
Mm-hmm.
And this is, so this is where I had to read this section a few times. Do you remember, did this come from somewhere else in the book?
I think this is like he's throwing the ball ahead on the field, and then he's gonna explain how he got there. But this is one of those given equations that we claim at this point, right?
Okay.
So yeah, I don't think there is the explanation for this equation before.
Okay. Well, this is the explanation here. But it goes into it basically, you have to know E in order for this equation to be true, due to the discrete log problem.
Mm-hmm.
Because of this right here. And I think this is, so EG equals P. So I think because of this is the same as E, right? Because EG equals P. So P equals this times G, so, right? So E equals that sort of thing.
Yes.
So we know E. So we can kind of like go backwards from E to get U and V with our random number that we decide. Right? Because we know E.
Mm-hmm. So U and V are like proxies for showing that we know E. You can present U and V without actually revealing E.
Yes. Yeah. That makes sense. And because I think, where was that? There was something. But yeah. Because they are equal, we can reveal these ones, because you can't go from the right hand here to the left. You can only go from the left to the right.
Mm-hmm.
Okay. So if we provide a correct u, v, we either have to discrete or no e. Since we assume discrete log is hard, we can say the e is assumed to be known by the one who came up with u and b. So that was another thing is I was curious what the u, like where do we derive the u and v from? And I didn't quite get that one until I got here.
Exactly, yeah.
Which, so we have the letter z, which is the fingerprint of the message containing the intent of the shooter. Or I think it's also, I think they also talk about it down here in the verification and debt. Yeah, so we're hashing the document with 2 rounds of SHA-256, and that just gives us exactly 32 bytes, and then that becomes our Z. So Z is the signature hash, hash 256, on the document. So that's where our Z comes in, right?
Mm-hmm.
And then, so we have the letter Z, which is
the letter S.
So the letter S also comes in a little bit down below, but so R is using the calculation of V, and R we know to be. It was a little. I thought it was there was a little R for a random number.
Yeah, R is like the X of big R.
Right. That's what we should.
Okay.
So we don't have U, but we know that U is not 0. We don't have V. We know that V is not 0. We have Z because we're hashing the document that we're using. And then we have R because R is the X value of the random point that we found by using a random 256-bit number. That is K. Whew.
So many variables.
Right. Yeah. And so we can calculate S. The thing that it doesn't say, I don't think, until what's that?
Sorry, I see now. So to generate R, we just when you go back to page 63. 63. So that equation Kg equals R.
Yeah.
So we only use K to generate R at that time. That's it.
Yeah, and that's why it talks about you don't reveal K. And it goes into this hard math here again. But it basically, if you reveal K, then you can reverse to your private key.
In K, from what I'm guessing, for each transaction, you just would use a creator, come up with a new K, right? Every time.
I think so.
And that's why it's saying like make sure you're using truly random numbers for K.
Right.
Nice. So then we use K to scalar. Yeah, one last time, go back to 63. So we're multiplying the generator point by K.
Mm-hmm. We're just going to use scalar multiplication.
And we're going to get a random number, but it's on the curve because we're using scalar multiplication.
Right.
On G.
Yep. Because we're going from that generator point.
We're just adding it a k number of times, and then we
And
land on this point.
and do you in the group of these numbers, right? Like the order is so large that it's like just pick a number.
Basically, like there could be a chance one in an atom in the universe.
Right.
Is a year. No, even that. If you if you if you were to pick a number at random that is exactly the size of the G group, then
Mm-hmm.
you would get infinity. You know what I mean?
Yeah. Infinity is part of that group.
Yeah, but that's the same as finding a private key. Same chance as finding a private key.
Yeah.
No one cares about that. At random, like just picking a private key. Okay. That was cool.
And then it goes through sort of finding S for us. And I think where was
I'll be right back. Cat number 2, what's up?
yeah, man, we got time. So with this, we're injecting E here, which I don't. Oh wait, because what equals P? P is equal to E times G, right? So this makes sense. All right, this is why I needed to write this stuff down, because if you look at this,
Yeah.
right? So we have this UG plus VP equals R also equals KG. So we replace P with E times G because we've defined that we've defined that already.
It's like our main function.
And then we can drop G entirely by just dividing both sides by G, which gives us this U plus VE divided or equals K, right? So U being non-zero plus V non-zero times our private key identifier equals a K. And then okay, let's think about this for a second. How do we get from this to this?
Just based on those two, yeah.
This here, yep. Yeah, we're just we're replacing U with Z divided by S and replacing V with
Z, which is our signature hash.
Signature hash, correct. And then RE divided by S because we had VE, so V becomes RS. And then because
R
is the random number, it's the random point on the curve, but the X value of it.
Okay.
Which gives us, which we can combine these two because they're both dividing by S. So now we get Z plus RE divided by S equals K. And then all we have to do is divide by
equation around,
yeah, it's not divide by, but it's you do the same operation, which is this to both sides. It cancels this out, but then it adds it over here. I don't remember the name of that, but that's because I don't have a degree. No, so okay, so that makes sense now, and so now we can get, and this makes sense too because we know like these are sort of known things to us, that we can derive S from these sort of known things that we're generating, right? Like we generate Z, which is the signature hash. We're generating R because we're picking a random point and taking the X value. We know E because it's our private key. And then
What's K again?
K is the random 256-bit number that we're using to generate the random point on the curve by multiplying that by the generation point.
So they're directly related.
Mm-hmm.
You change one, you're gonna change the other automatically.
Right. And so now we can get S, which I still don't know what S stands for, or what its significance here, other than calculating. What do we calculate? Calculate U and V using S.
The two numbers in the signature are R and S. It's kind of like a quotient. Is this like just?
What do you mean?
Yeah, like a coefficient. I think you could say. Since you have all those numbers defined, yeah.
Well, and we should take these out and put these in our definitions here so we can reference them easier. Because this verification point, or this verification part, so we have UG plus VP, and if we substitute U, we get ZS, and we substitute, this substitutes two things. This substitutes V for the R divided by S, but it also substitutes P where it's E times G, right? And then that allows us to combine the two and just divide by S and then multiply by the generator point. And then this is... Let me see. What are we substituting? Okay. So this we're replacing S with this algorithm here. So now we get the Z plus RE twice. Well, not twice, but it's like this is now S, right? Because it's replaced.
And then you have a fraction on top of a fraction, which then just becomes K.
Right. Yes. Yeah.
Wow.
Which gives us R and Y. What is Y? Where did Y come from? Or no, that KG, that's the generator point.
Oh, we're going back to...
It's X and Y. Yeah, X and Y. But the R is the X of the random point. Okay. See? Okay. Man, don't ask me to do that off the cuff.
So this is the verification, like not for someone to verify a cryptographic signature because you're revealing K there. Or is it verification
Well, you're not.
just for us?
It's just for us because I think you would only reveal this, right? Because that's the
that is R, uppercase R.
Yeah. Which is our target, right?
It's R.
No.
Yeah.
It might be our target. Yeah, hold on, let me. Yeah, R is now the target we're aiming for. So yes. So R is the target we're aiming for. Z is the purpose of our shooting.
Purpose meaning this is the signature hash.
The hash, yeah, what we're hashing to sign. Yeah, so this is equal to R even. So the lowercase r comma y is equal to the uppercase R, which is our target. All right. And this goes way in depth on it. It talks about the hashing to get to Z. It talks...
How's that?
What's that?
Okay, like that it has to hash twice.
Right. And so we still have the S signature, or the S formula for getting to it. Keep in mind that we know E, and we know K, and we know Z. Oh, we kind of just went over all this. This is the verification in depth. Yeah, this is that big long equation that we just did up here. Kg equals a random number.
No, which then he actually put exactly what you were saying. Kg equals R.
Right.
We've successfully chosen U and V in such a way as to generate R as we intended.
Yep. And this, okay, and so I think this is one of the key things here. The only way we can know the details of R beforehand is if we know E, because E is a function, or is a parameter in the formula to get to R. Does that make sense? And it makes sense when you think about what E is. E is a private key. So we're using E to generate. We're using. No, hold on a second.
Yeah.
Because the random point X needs to. Oh, here we go. Let's read these steps and see. So we're given R and S. So random X value and S as a signature.
R and S. So let me just refresh my memory. So R, lowercase r is the X coordinate of our generated random point.
Right. And S is the signature. Oh, okay. That makes sense. So S is the signature, which we generate to use E. We have Z, which is the hash of the thing being signed in the public key or public point of the signer. So because we have S already, we can get U and V. Oh, okay, yeah, because it's validation. So that's why it's so like recursive, where it like references back to each other. If that makes sense. So we're already given the signature. The signature is what we're giving, right? Because the signature, we're just verifying right now. So we're provided
we are
R and S. Yeah, okay. We're given the signature.
If you're someone that received a message and you want to confirm that it came from the person that has the private key.
Right.
That's who we are right now. Right?
Yep. And then
so you get R, lowercase r, S, because S, as you mentioned, S can only be calculated through that equation that includes the private key.
Right. And this is going from this is like proving we're signing something to prove that we own a public key. And our public key is generated, right? Using E times the generator point. Now, how does that work? Because the generator point is constant. So how do you get a different P every time? Or is that, oh, you know what? I might be overthinking this. That might be like the XPub, like your main, your master public key. You know what an XPub is?
Yeah.
Okay. Well, you've got it down more than Peter McCormick.
You don't want to.
But you're
review your XPub. If you review your XPub, you can see all the heuristically.
Yeah, so all of your addresses are generated from your XPub. There's like derivation paths and stuff that go into that, and I think we'll learn about that later in the book. But I'm overthinking it in the sense of I'm thinking of public key as in like addresses that are generated from the public key, but when in fact
Mhm.
when you have a private key, there's only one public key that matches that private key. That's part of like the asymmetric cryptography thing, right? There's one private key, there's one public key. Now all of the addresses are derived from the public key. So this calculation makes sense again to me because you're only going to have one P for each E.
Okay.
And the way that we get to
Which
the
is yeah,
P,
before BIP 39, right? Was it BIP 39 that brought up the HD wallets, right?
oh yeah, I see, I don't know. What is it? BIP
So BIP
39?
39 is the mnemonic seed phrases. But yeah, the DHT wallets, right? 32 maybe. Yeah, BIP 32.
BIP 32?
Hierarchical deterministic wallets.
See, I haven't gone down that rabbit hole.
I haven't. Yeah. So yeah.
Child key derivation function. Oh, that's interesting.
Oh, there's many multiple depths.
Yeah.
That's very
Well, now I kind of know because it asks you for your like derivation path
cool.
in the wallet that I use. And
Yes.
that's something I've heard mentioned before. It's like people will like use some weird derivation path to try to like be super sneaky and stuff, and then they forget it and they're fucked because they can't find their money.
Yeah, I don't go too deep into that, but yeah.
No.
So M. So that's what it is. So the slashes are like you're going deeper into the tree.
Right. Yeah. Yeah. That makes sense. Phew.
But yeah, as you mentioned, like for now we're only looking at the master seed, really,
Well,
not the node.
and it's created from the pub key.
Which is the XPub, yeah.
Yeah.
And then yeah, we're not even getting into that soon, probably into like Y pubs and Z pubs.
I don't even want to know about those right now. I'm not ready for it.
Me neither.
Um.
We know they're there.
Yeah. 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 So that's cool. Okay. And then we go in and do all this fancy math, and basically it's just validating the signature. It's validating the signature for the hashed content, right? Like that's what we're doing. Um. And then it goes into coding for that specific verification of the signature, which we didn't get to yet because we haven't refactored.
Yeah.
Wow. Okay, that makes a lot more sense now. That was. Thank you.
Yeah.
Yeah.
I'll still have to uh, go through it a few times. But yeah, writing down the variables helped a bunch.
Yeah. 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 Um. So I mean, I guess we can talk about signing a little bit too, if we're not going to get to, unless you want to get
Yeah.
back into the refactoring.
Yeah. Maybe yeah. Let's go. Let's keep going with new stuff.
Okay.
Then we can do some refactoring as well.
So we know how verification works because we just talked about it. And the last, I guess we should probably copy like what's the verification algorithm is. Um. Here. Yeah, we're given R and S. Let's see. We already have that, so this right here is what we need. Cool. But it talks about signing, which is so signing. We start with a signature hash of the document we are signing, and we know E. because that's our private key. And so we choose a random K, which makes sense, which is a random number, 256-bit. And then what we calculate R, which is K times the generator point. And then that's how we derive the new lowercase r. And then we can get, S. Because S is the hash plus the random X coordinate times the private key divided by that random number that we used to generate.
The random number is influencing two factors in this equation, right?
It's influencing S and R.
And K, right? Because K is the actual random number.
Right. Yeah, K is the random number. Yep.
Yes, it's everywhere. Random K, that's so interesting. And the signature is a point as well.
And this is interesting. It says Z is computed. And that makes sense because I imagine I'm guessing at this point because I don't think I've read beyond this, or maybe I have, but it says Z is computed, so you just have to send P with the with the signature. And I'm guessing that's because Z is just a hash of the document, so you send the document plus P. Or maybe P's even included in the document with the signature. And so if you have
It's like when you're downloading a package online and they give you the private key to check the package, right? Z is the actual file,
right?
And then you can hash it.
Well, no, Z is the hash of the file.
Z is the hash of the file, correct?
The 32-bit hash of the file. And so if you have the file or the document or whatever, then you can calculate Z yourself.
Yeah.
And then that can make sure that, whatever you signed, right? Because if you sign something that's Z, and then I send you a document and somebody malicious is in the middle of our conversation and decides that they want to modify the document in any way, when you go to calculate Z, your math will not work. Right?
Mm-hmm. And it's important because I always think of that. You're downloading something on a website.
Yeah.
And they'll give the hash and the signature. So if a malicious actor were to change that file, they might as well change the hash and the signature, right?
Well, yeah, that's another thing too, is like websites. Right.
Generate.
Yeah.
And I think that's where it comes, like if you're on PGP, these signatures, they have been created and published like years ago. So then I know that Gary's signature was published like in 2015. And I can trust that signature has got reputation, it's been around for a long time.
Right, yeah. Unless you get your signature compromised.
Then that's a big problem.
Yeah. Yeah, and then it goes into us computing signatures. Cool.
Jimmy is not recommending using the random library, the little scorpion above.
Yeah.
Not really random. Not random enough.
Not for production. Maybe on testnet. Definitely on testnet.
Yeah.
We're gonna send a testnet transaction, right?
Yes.
That's part of the book. So yeah, I mean, once we have signatures, now we can start signing whatever we want, right? Because we just input the document that we want to sign into what we're the hash, or we input the hash of the document that we want to sign into the signing algorithm that we just went over. This goes over that unique K again. So you don't want to reuse K. Um,
Oh yeah.
and this is kind of highlighting why you don't want to use like a crappy random number generator. Like you need to use like a really good one. Because if you reuse K, then people can like figure out your private key.
Oh wow. So someone can like cross-reference two signatures
Yeah.
and derive K
Right.
from it.
Yep.
Uh,
And that's this the PS3 hack, I guess, did that.
uh,
They were using the same K.
ECDSA, the same
Yep.
uh, signing algorithm.
So Sony was not randomizing the signature. But
No, they were
oh, what's
they
that?
were using the same number every single time.
They were using the same K. And so okay, so let's go through this cuz we know the so this is given that we have what, two values or two S's or two signatures, two parts of a signature, right?
Z1 and Z2, yeah.
And so KG equals RY. Let's see what this goes. So S, where does S? So S equals Z plus REK. And this is both of these, the two different ones.
They're like running them in parallel.
Right. Oh, so by removing K, or it basically eliminates K and it compares these two divided by each other. Oh, I see. So it's taking the S value or the S value with the hashed document plus the random plus the private key and basically swapping them like 1 and 2 and 2 and 1 sort of thing.
Hmm.
And then it eventually all goes back to your private key and no more money. I don't exactly follow it, but I see how like it can combine the two. Using those math properties that I forgot from high school.
Yeah. Distribution or something like that.
Right, yeah, it's like doing this one thing to one side of the equation, you have to do the other side, and it like removes from one side and adds to another sort of thing.
Elimination.
Math. So that's cool.
So that's why, yeah, you don't want to use Python, a simple Python library, because after you send maybe 1,000 transactions, you give a malicious actor enough data
Right.
to test.
Right.
Because all it takes is two signatures with the same K for someone to derive.
I think it's gonna take more than that. I think this might be simplifying it. Maybe not. I don't know. Yeah, no, I guess you just only need the two
Yeah,
signatures.
that's what it seems. So then, yeah.
Two signatures
Then
for the same was this even the same Z or no?
I don't think so.
It's not even for the same document. What is similar? Just K.
Just K, yeah.
Huh.
Wow. Gotta randomize that K.
Somebody got fired at Sony, I'm sure.
And of course, yeah. Because you have such a huge sample size for K. 256-bit K.
Yeah, that's a lot.
They're gonna pick the same K twice.
This is the RFCs. Have you seen RFCs before? They're very dry documents.
What's the name? Like a protocol, right?
Yeah.
Yeah, how they're defined.
Yeah, I think like HTTP and like all of there are a lot of RFCs that are out there. An RFC is just, I think it's just request for comment. It's like what
Oh,
the acronym breaks down
so
to.
it's not- oh,
And that's because people will put out RFCs of like, hey, you know, comment on this sort of thing. Yeah,
even
here's
after they've been commented enough.
official internet protocols. But yeah, it's just very,
And
very dry. If you ever want to learn about subnetting procedure,
that's the
it's
go-to.
all out there. And look at this, 1985 ARPANET
I was
specifying
1 month old.
what? I wasn't even a twinkle in my parents' eye yet. I don't even think my parents had met.
Are you the oldest?
I am the oldest, yeah.
Yeah,
You got me by 5 years.
nice. I'm the youngest.
Wait, you
So
were born in July?
yes,
Which day?
20th.
No fucking way. Are you serious?
Yeah.
That's my birthday. That is awesome.
Amazing, dude.
That is okay. All right, we might have to have a birthday party together.
We should, yeah, we will.
What?
Man,
We need to stop the stream.
that's cool.
I don't know what to do. That's so crazy. That's great. What are the chances?
We were just talking about hitting the same K
Yeah,
on
oh
stream.
no.
That's
Wow,
amazing.
that is awesome. Okay.
Nice. So
Awesome.
that's why you need good random numbers. You see,
Yes.
these collisions do happen.
Well, what is it? It's called the birthday problem or whatever, and it's like
Like the odds or
yeah. Probability theory that two people in the same room will have the same birthday. Or the probability that two random Bitcoiners that met on Twitter that decided to do a weekly live stream together would have the same birthday. What's the probability of that? Somebody please figure that out. That is too wild. And we didn't even have, what is it? What do we need to get? We're way down here on the curve.
yeah. Wow. That's gotta be it. Probably not. No other Bitcoiner
No.
that's like doing something similar right now.
I can't imagine.
That's
Um,
so cool.
yeah. Anyway, I think we should go into the refactor because the next is going into serialization and that goes into byte level stuff
Mm.
and like marking things in bytes to like this is always the stuff that fascinated down at low levels because it's like you would prefix things with like certain markers and it would make entirely new definitions or meanings for the following bytes. But let's
Is it
get
kind of like in a much simpler fashion? How do you say like when you have encoded emojis, UTF-8 or something like that?
um
Yeah.
yeah,
Because I know
probably.
there's a lot of byte, like one byte's gonna say something, another byte's gonna say something else.
Well, okay, so I think the simplest explanation of this, or the simplest like example of sort of like the first bytes determining, um, so let's see if ChatGPT 3 can explain this better than I can, because I've got an idea in my head, but I'm not quite sure if I can articulate it.
Mm-hmm.
Okay, log me in, please. I have a dark basement, and there's a cat making sounds somewhere in the background. Oh
Getting
shit!
ready to
Pounce,
jump on you.
you know it.
Speaking of cat, I'll be back in a second.
All right. Um, so I'm thinking about like signed integers, like an integer 64, right?
Mm-hmm.
So it's using its most significant bit as
So it is the one to the left.
I think, unless it's okay. So yeah, I guess it is the one to the very left. So what is? Do you remember what big endian and little endian?
I didn't know, but you brought it up a couple weeks ago, so I did some research.
Multi-byte values.
Like that it is about the bytes,
Oh,
not the bits themselves.
right, right. Okay, the least significant byte is stored at the largest memory address. Oh, it's the way it's storing it in memory.
Yeah, the groups of 8 bits or something like that.
Okay.
Remember, like Windows, I think it's little endian.
Which one does Windows use? ChatGPT will tell us. Little endian.
Yeah.
Okay, there we go. All right, let's stop messing around with AI and let's do the thing that neither of us want to do right now because we're procrastinating. is refactoring. We can save this.
Yeah, this is good.
Signature. All right. So we've got a whole lot of. I think it was mainly in the point. Let's hold on. Let's check and see if our field element tests all pass. I don't know if we migrated them to use big wints. No, we did not. Okay. So we'll have to migrate that, or migrate all of these really. Yeah, because everything's going to be a big win now. Maybe. All right. How do we define? How do we create a new big win? I know it's got to be up here somewhere. Oh, I guess not. All right. Oh, see. Bounded is not satisfied. Okay, so we got all kinds of errors in here that we can refactor. So that's fine. Let's get to some refactoring and see how far we can get.
Mm-hmm.
Um, let's see about. So how? Okay, so there's a new. But let's look at the docs to do this. Might be a better idea. It's been a while.
A lot goes on in a week, right?
Yeah, it does. I've been uh, very interested in Nostr.
Nice.
So you give it a vec of unsigned 32-bit numbers. Is there a... Oh, wait. I think from... I thought there was...
What was radix again? Was it hex?
No, radix was...
Literal.
No, radix is another name for something.
Yeah,
It's the base of... It's the base... It's like the base 10 is what we use. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, the base of a system of numbers.
Okay.
So you could yeah. So I guess this is base 190.
Very, very common.
Right.
Everybody uses it.
Right. Oh yeah, and goes into the Endianness of it.
Little Indian, yeah.
Yeah.
Big Indian.
But man, that's okay. I'm just gonna go back and I've been using ChatGPT 3 for like asking just simple programming instead of clicking through a million Google results.
Just ask it.
Yeah. And it usually gives me just wonderful results. Oh, you just do an into. So that's easy enough. I forgot about that. The into trait or the into. Okay, so do you want to go through here and maybe start at the bottom?
Okay, so
of the tests.
do we want to refactor the test? We do, right? Because that's how we're gonna test if it's actually working.
Right. And we will do. I think so. I'm pretty sure.
Okay.
We'll see if. Let me see if. Yeah, I don't get any more arrows, because the into function just like converts it into an inferred type. So it tries to convert it into whatever type it needs to be in order for the program to work.
And you already defined field elements as big uints.
Right.
Above, and that's why. Okay.
So the compiler knows that, like, hey, I'm trying to coerce this into, into a big wint
type of number. It's
right,
specified.
and it's whatever type either. Like, I mean, you could, if you have a type or anything like that, it's
an array and a dictionary, whatever.
Right. Power of VS Code Live Share. I'm gonna start from the bottom.
Oh, okay, yeah. Thanks. I have some problem with the power of.
Yeah, we're gonna have to refactor some of those.
Okay. Yeah, let me see if it accepts the big uint. Okay.
One more. I'm hoping that it's all right. So, what's going on here? All right, so it doesn't like into.
Just took a.
It's not. Oh, okay. All right. So it's because the compiler thinks that the numbers are signed integers. So that's why in the example that ChatGPT 3 gave us, you do like a U64 to tell it that it's
right after the number.
Right after the number, yeah.
Okay, let's start from the bottom.
And that should do her. So we're looking at Costa Rica in March.
March, like 2 months from now?
Yeah.
Nice.
We'll see.
How long?
Like a week. But mainly for the Nostr conference.
Ah.
Yeah.
See what you were up to.
Oh yeah.
Nice.
All right. Now let's let the Rust Analyzer catch up. See if it's
Oh wait,
happy.
there's a to the power of that was missing. Week 64 dot into. Okay.
Nice. Nice, nice, nice. Oh yeah, and
There's
it's
some missing still.
okay. So Rust Analyzer, it's catching up to us right now. We're just gonna run. We're just gonna run cargo test, and we'll do field. That should only test our. Okay. All right. It doesn't. Okay, so this is good. We've got what's going on here. We've got
37.
oh, okay, so we found a U64. It needs a big wind.
Okay. That's part of the to the power of that.
There's something here too that is. Oh, this is gonna be U64. Oh man. Oh, okay. So that's not.
Is it because you're doing as U64 after?
It's because it can't infer the type.
But isn't it because is it casting as unsigned 64 here?
It's
Right where I am here.
Oh, actually, yeah,
Right.
yeah. You might be right. Yeah, delete that.
Yeah, like we were casting as Uint and then casting it back as U64.
Right, right, right. Now we can delete these. Delete that last parenthesis there.
Okay.
Good catch.
So that's a subtract.
That's
Subtract
oh,
not implemented for big Uint.
is the oh, that's because this is an option because we're using the from U64 like it. That's weird. If the value cannot be represented, then none is returned. But like a U64 is always going to fit in a big wint, so that's weird that it would give an option. But I'm sure there's a valid reason for that. We're just going to unwrap it.
It's not related to infinity or zero, right?
Maybe? I don't know. Because there should still be a 0 point. So there's no infinity in U64, right? Because you can only represent so many spaces in 64 bits. Or such a big number.
So remember we were using the options for the infinity, right?
Yeah, no, I don't think it's related to that. So
Okay.
like uint, a big uint or unsigned integer is just like a really big integer, like as big as you can get. A U64 is an unsigned integer that fits within 64 bits of memory space, right? So that's only so big because if you put all the ones, right, like, and I think there's even like U64, U64 has maybe it's lowercase max, right? So like U64 has a max value that is just this number, right? because that's the biggest
Okay,
value that
yeah.
can be represented with that many bits.
Just not that big in our with what we're working on, what we're working
Right,
with.
but what I mean is this was complaining. So this from U64 has an option. When I see an option, it means that um, it's like it could fail. And I mean, we can click in and see the source code of this as well.
Hmm.
Oh, it always returns a sum. Interesting. So that's weird. So
No,
you
so it wasn't the sum we were using for infinity. It's a different sum. Yeah.
it is.
So
It's
yeah,
the
what
option
would
sum, but it doesn't even. It never. It like the option is never returned as
none
none. So that's weird to me. Why wouldn't they just return?
the actual number, right?
Yeah. Let's not. I don't want to. That's not a problem I care to solve today
Yeah.
or
Why are we getting so
understand.
many problems now? We're just going up now,
Right.
non-stop.
Um. Oh, you talking about down here? All the
Uh,
errors we have.
yeah.
That's because we have this mod POW that we haven't updated yet.
Oh, okay, so there's just more refactoring to do.
Mm-hmm.
Let's do this. Okay.
So I think actually I think Big Wind has a 1. Or is it just a 0? Yeah. Oh, it does have a 1. Yay. And then here we would return Big Wind 0. And then we could replace this with Big Wind 1. And what is our exponent? Is also a Big Wind. Replace with this 0. I don't know if this is actually going to work. And we need to replace this here. And I'm assuming that this is complaining because, yeah, this wants to be a Big Wind as well. So we'll do some more type coercion. Does that not work? Type must be known. Okay. So we'll have to do the same thing. It just doesn't like that type coercion. We can do from U64. And it still doesn't like it. Something else. Oh, and then we have to unwrap it. Oh, that's so ugly. So much extra code. There's probably a more elegant solution here, but we're just going to try to get to where we have 0 errors in this
So to
file.
cast, like number 2 in Big Wind, you're having to use the from U64, then you type 2, and you tell that it's a U64, and you unwrap it.
Yeah, because it's a option.
Because as you went back into the code there, you saw that it always generates an option.
Yeah. Yeah.
Okay. Looks good to me. That's it?
I
No
think.
need to do
No,
one for
here's
that
some
one, right?
more. We have subtraction now.
Okay.
So I think we just delete this part though. Like we just don't need to tell it to be an I64. We just tell it to be a Big Wind. Same thing here. Oh, this is going to be... All right. So this is... we can't use... So I don't think we can use Big Wind here. because we have the potential of having a negative number.
Unless they implemented this Euclid function for big wind.
Yeah, but we still Okay, so there's a big int type. We'll check. That's a good call though, that they might have that that function, the remainder Euclidean. Oh, okay, cool.
With the same name and everything.
Of course. So we just needed big int. Nice. Maybe. So we need to go from big gwint to big int. And I think it's probably just doing like a into, if I had to guess. Yeah, the from trait. So let's see if this works.
Big wind into big int.
But all right, so
big int into big wind.
Right, and then back. Okay, so it doesn't actually have a
Euclid.
Yeah, we're probably gonna have to look up. We're gonna have to probably look up the docs on this one.
Isn't it because you're browsing the big wind options there? It's actually big int that has.
Well, this is a big int. So difference is a big int.
Yeah, but the new number, difference is a big int. Okay.
Yeah. So I think we are gonna have to go check the big int crate documents to see that remainder function. Big int remainder. Forms the modulus operation.
Another word to use, but the fact that we were born on the same day of the year. That's
fate, dude. Fate. Like I don't know. Higher powers. Yeah. It's pretty crazy. Hey, here's all my Google history.
To the world.
Yeah. Big int Rust Euclidean modulus. I think this is the one that we looked at before.
Hmm.
What is this num modular? This is... Okay, so this might be a interesting crate to check out. Num modular. We might just have to... We might have to find... Yeah, we might have to figure out a way to do that.
It's funny. I'm gonna share an address with you on Discord.
Okay.
I feel like Big Ant does have the RAM Euclid.
Is it just called something different?
Look at this. Yeah, look at this address I sent you. It's the source code for Big Ant. Like line 484, for example.
Hey, okay.
I don't know. Maybe.
Good Google foo here.
Yeah.
I checked Euclid.
Yeah, then normal Euclid. And there you have
RAM
Euclid.
Yeah. Oh, this is an open PR.
Oh, it's an open PR.
Yeah. Now that I come
so I mean, you could merge this with your Big Ant that you have locally.
We could, yeah. Interesting. I wonder why.
Or just copy that chunk into.
Yeah, that's what I was thinking about as well.
Yeah.
Oh. Okay. Let R. So V is a big N, so self divided by, and then if R is less than 0. Oh, because of big int, we can go negative as much as we want. So if R is less than 0, okay, cool. And if V is less than 0, V being the thing we're modulusing by, which it won't be. V will never be, for us, V will never be less than 0. So it's just if, okay, all right, yeah, that makes sense. All right, we can just do this ourselves. That makes sense. So we have the difference here. So remainder equals, so the difference,
Boolean. Remainder.
I'm sorry?
Oh, okay. Sorry.
Yeah, it's going to have weird type stuff. Just yeah. And this is going to be self.prime that we're modding it by. And we should be able to just coerce that into all right, we'll hold on. We'll do this. So that way Russ is happy with us. Right? So we do that. And then oh man, what is it? There's like a it's a Rust pattern, and I'm blanking because it's getting late, but it's like an if-let pattern, and it's if-let, and this is the condition. Man, okay, I'm gonna have to look it up. This is there's an if-let pattern, and I can never remember the order that things happen. It's all right. We're just gonna do a regular if statement because I can't do this. I can't do thinking right now. And this might be once we get this file good, we're gonna call it.
Yeah, that sounds good to me.
But where was that? Where did that PR go? Here we go. All right, so it's the remainder big int 0. Okay, so
yeah, so it's nesting too.
Yep, and our v is always going to be bigger than 0. So this is false, right? Because v is not, and so remainder plus the prime.
V is the what is v?
V is going to be the number that we're modulating by. So in this case, it's the prime.
Okay.
So in this case, it would be.
So you don't need the second if statement because you're always landing on false there.
Right. Yeah, we don't need that second one because we're guaranteed because we're coming from a big wint, and our self dot prime is always going to be positive. Perfect. We just do remainder plus the prime, and then that's our. Otherwise, it's just the remainder. Yeah, it's just.
Remainder. Oh, nice.
Right? Yeah. Yeah, because this just gives us the remainder. And then we're just checking. We're just checking if the remainder is positive or negative. What is it? What's this complaining about
I'm
here?
guessing you have to recast that remainder back to big uint. Oh, you're looking at the other one. Okay, we'll get there.
Oh yeah. We will have to do that. Yeah, because this is going to be greater than 0, so that's fine too. We can just do an into, I think. Nope. Okay. From, and this should give us an option that we're going to have to unwrap.
And I'm probably going to have to do the same thing
here. No, we're not unwrapping the remainder though. Wait, and this is not.
Thinking about the addition here.
Oh, so there's problems. Okay, so going from big int to big wint. Because the big wint doesn't have... Oh, try into. Interesting. Let's see if that works.
Just try it. Yeah. Might work out in the end.
All right, so that worked. Try into worked. But
you know it's not gonna be negative, so there's no risk.
Right.
Working.
Yeah. And we also know at this point too that the remainder plus the prime is going to turn into a non-negative number, but in this case the remainder is negative, so we're going to have to stay... Oh man, we're going to have to stay in a big int. Let's do this. Let's not do... Hold on. Let's not do this inline here.
Okay.
And because we're going to do this too, we're going to create a new variable just to make this easier. Like this. And then we can reuse this variable here and here. Right? And so now we can do the new number try into, and it's safe to unwrap because we know that we're positive again. And so we're good to go back to a big wint.
Because if it's less than 0, then you add the prime to it. Because you modded by the prime before, when you add the prime, you're for sure gonna go.
Yeah.
You're gonna get to a positive number.
Right. Okay, this is... Where's this error at? Okay, what are we doing?
It's division.
Yeah. This is it's yelling at us. No implementation. Oh. So this is the modular exponent function. I don't remember where we got that from.
Me neither. I remember we had in Python we had the one with the 3 parameters.
Right.
And you figured out. I think you found it online.
Probably.
Like that.
Let's see what ChatGPT 3 finds for us. I'm sure it'll find something. Okay, so there's a POW method. Okay, so mod POW apparently is something that Big Wint has. So let's figure out... So based on this... Okay, so we're mod powing to self.prime minus 2, and then the modulus is self.prime. Okay. But that's going to be divisor... Yeah, it's not a real function, ChatGPT 3. Oh, wait. Num. Modpow. Okay, it is. All right, we're good.
There we go.
We're good. And so the exponent is... This. All right.
How'd you know it was num.modpop?
That's because num was we called num before. We did mod exponent